Okay, let's start.
All right, so we have a matrix. It's Q Hermitian if AH equals negative A.
Mm-hmm. Mm-hmm. Okay.
Problem 1. Okay, so a matrix is Q Hermitian. So a matrix is Q Hermitian if AH equals negative A. I don't think I am satisfied with that definition. What is a Hermitian matrix? Even without this Q.
Even without this Q? What's Q? Oh, you're talking about this Q.
Yeah, just Hermitian. So we can write a note. And then we can say that so Hermitian matrix, Hermitian matrix is a complex square matrix that is equal, to its own conjugate transpose. So that is the definition of a Hermitian matrix, even without it being skew.
Okay.
Yeah. So example, it has to be square. So let's think of a 2 by 2 matrix. So we could think of
oh, it means AH equals A transpose.
yeah. So let's think of a 2 by 2 matrix. We can think of 3 plus its own conjugate transpose. So let's think of P, and then we could have A plus IB, and then we can have A minus IB, and then we can have Q. What is the conjugate of this matrix? It's going to be
conjugate
P,
of this
A minus IB,
A minus IB,
and then A plus IB, and then Q, right?
It will be minus A minus IB.
No, it's going to be A minus IB. You know, whenever you're doing conjugates, you only negate the imaginary part.
Okay.
And then if you transpose it, you do a transpose on it, it's going to be P.
But
then,
in case if it's conjugate, do we need to change P and Q?
No, we are just assuming that P and Q are real. Yeah. So you know, a complex number, whenever you're doing its conjugate, you negate the imaginary part. So in this matrix, P doesn't have like an imaginary part.
Yes.
It's real. So if you do, if you transpose it, it's going to be P and then A plus IB, and then you have A minus IB, and then Q. You see what just happened? When we
Yes,
did
it's
a conjugate
transposed.
transpose of it, it gave us the same thing. Okay, and so that is just a Hermitian matrix. So it can only be skew Hermitian if we get the negative, if we get negative A. So this is an example of Hermitian. So this is just Hermitian. So example for the skew Hermitian, let me look up an example for a skew Hermitian matrix. Okay, let's think about you know, it's not easy to create such a matrix. Okay, so let's think about the same matrix, maybe.
Maybe we can use the solution. I mean, maybe it will be easier.
The solution doesn't have an example.
Oh yeah.
I was thinking
this.
of an example. Yeah.
Yeah, of course.
If I fail to get one, we can just leave it. Okay. So let's try this one. 0. And then you have -2 plus I. And then you have 2 plus I and 0. So let's find its conjugate. It's going to be 0.
0 minus 2
minus I.
minus I. And 2
and then
minus
this is 2 minus I.
0.
0. And then we find its conjugate. No, it's transpose. 0.
Transpose 0.
2 minus I.
2 minus I and -2 minus I 0.
You see, if this is A, then this is a skew Hermitian, -A. So in this case, this matrix is going to be skew Hermitian. I just wanted us to create a background before we start looking at the question. So now we can look at the question. So a matrix is skew Hermitian if you find its conjugate and then you find its transpose, you get negative.
Sorry, Steven, hold on. So A, it's a skew Hermitian matrix, right?
Yeah. This second example.
But it's not. So what's the difference between skew Hermitian and Hermitian? Hermitian matrix equals to the A transpose.
So for the Hermitian, if you do A and then you find its conjugate and then you find its transpose, you're going to get the same matrix A. You see what happened? We started with this and then we did the conjugate and then the transpose, we got the same matrix. You see, we started with a matrix A and then we ended up with the same matrix A, right? But now for the skew Hermitian, let me call it B. We started with a matrix B, but what did we end up with?
It was a negative B.
We got negative B. And that's why we say that it's going to be skew Hermitian if you take B and then you find its conjugate, its transpose, you get negative P to be your answer. Yeah. So the second example shows skew Hermitian. The first example explains Hermitian.
Okay, got it.
Yeah. So we go now to the question. You need to show, so show that a skew Hermitian matrix, a skew Hermitian matrix, A has purely imaginary eigen values. So by purely imaginary, we mean that the real part of each eigenvalue is going to be 0. Okay. So we start by the definition of an eigenvalue. So let's do the solution. Remember, I told you an eigenvalue is a real number that's going to behave like your matrix for some vectors inside your space. So if you take A multiplied by some vector X inside your space, you're going to get the eigenvalue multiplied by the same vector. So the eigenvalue is like a scalar representation of your matrix. So that's the definition. And then we also know that by the definition of skew Hermitian, we know that A, when the H means you take its complex conjugates and then you transpose it. And if you do that, you're going to get negative A. And also one more thing, it must be a square matrix. And that's why we are saying that this matrix is going to be contained inside the n by n space of complex numbers.
Yes.
Yeah. All right. So you have your solutions with you, right?
Yes.
So the first step, he's just multiplying by xh. So he's taking a vector. Xh means that he's just taking a random vector, its conjugate, and then its transpose. That's what he's doing. So this fact, ax equals lambda x, it means we can just take the vector x and then we find its conjugate and then we transpose it. And this is what we are calling xh multiplied by a x. And then this is going to be equal to lambda
X
xh multiplied by x. Okay. Yeah. So if we divide both sides by xhx, we are getting that lambda equals xhax divided by xhx. So what do you think about that denominator that we have there? let's take an example. I want you to assume that, let's assume X is something like 1 plus maybe 2i, right?
Mm-hmm.
And then maybe 3 plus I. What will be XH? You have to take its conjugate.
Transpose, yes, to take a conjugate, it's 1 minus 2i.
1 minus 2i, and then you transpose it.
3 minus I.
3 minus I, right? And then if you do XHX, it's going to be 1 minus 2i, 3 minus I,
minus I
multiplied
times
by 1 plus 2i,
1 plus 2i,
3 minus I.
3 plus I.
3 plus I, thanks.
Mm-hmm.
So this is going to be 5. That's going to be 5. Plus, this is going to be 10. You see, it's 15, right? So in short, I was using this example to show you that if you take XH multiplied by X, you will always get a real number for your answer.
Okay, let me write very quick this example.
So
Mm-hmm.
this example shows that XHX will always be real. Will always be real.
Mm-hmm.
So let's do it in an abstract way. So, oh, I hope you finished writing that.
Yes. Yeah, go ahead.
Okay. So with that example in mind, you're going to realize that XHX equals summation I running from 1 to n. You know, this is the complex conjugate. So it's going to be xj, the elements inside x squared. Okay. You see, whenever you take a complex conjugate, a plus bi, if you multiply it by itself, if you multiply a complex number by its conjugate, you will always get a squared. A squared plus
minus
b
s
squared,
because I square.
Yeah. Now this is what we are calling xj squared.
Okay.
Yeah. Oh, and they have written it. They have written it there. So it's going to be the sum of j running from 1 to n, and then this is aj squared plus bj squared, and it will always be a positive real number. Okay. So what does that tell you? This tells you that we don't need to worry about the denominator. So lambda equals xh ax divided by some real number, divided by k, where k is a real number. Our objective is to show that the lambda is going to be purely imaginary. And because we have stopped worrying about the denominator, we only need to show that the top part is going to be imaginary. Okay.
Okay, only top parts should be imaginary.
Yeah.
Mm-hmm.
All right.
And okay.
And remember, lambda is a scalar, right?
Yes, it's real number.
Yeah. So since, no, not real. Since lambda is
Scalar.
a scalar, a nice mathematical way of saying that lambda is a scalar is just saying that it's coming from the field of complex numbers. Okay.
Mm-hmm.
And since
Okay.
lambda is a scalar, then you're going to agree with me that the numerator, the xh ax,
Mm-hmm.
it also has to be a scalar, right?
Agree, yes.
So if that has to be a scalar, then xh ax has to be equal to some number p plus iq. It has to be equal to some number p plus iq, right?
Mm-hmm. Mm-hmm.
Yeah.
Why we need to use this? Okay, because it's complex. Okay.
Yeah, because it's a complex number, so it has to be some number p plus iq.
Mm-hmm.
Yeah. Okay. Now, this is a matrix, right?
Mm-hmm. Which one? A? All of them, yes, this is a matrix.
It's actually, it's a scalar. It's a scalar p plus iq.
Mm-hmm.
Yeah. And we know that a is equal to negative a as well. That's what we know.
Yes, because it's Q Hermitian matrix.
Yeah. And so because a is equal to negative a, we can say that x h ax is equal to negative x h ax. We have all the right to say that.
Mm-hmm. Yes, I agree.
And so let me call this statement star, and then I will call the second statement star star. So if you look at these two statements, so from the first statement star and the second statement that I choose to call star star, we can conclude that p plus iq equals p minus iq, right?
Yes.
Equals p negative p minus iq, because this is equal to this and this is equal to its negative. So p plus iq is also equal to, let me write it like this. Let me say p plus iq, it's going to be equal to its negative. So negative p plus iq. Let me write it like that. Okay. And so this is going to mean that p plus iq is equal to negative p something is missing.
You're doing right.
Yeah, but
Oh,
I
P
missed
minus IQ.
I missed a very important step. So we have XHAX equals negative XHAX. Okay. So let's also, okay, let's keep this. So XHAX equals that. Okay. So looking at the first statement, we can also say that XHAX, we can do a Hermitian on this. Equals P plus IQ. We can also do a Hermitian on that, which will be equal to P minus IQ, right?
I don't know. Yes.
Yeah. Okay. So if we do all these Hermitians, let's open this bracket. Realize that this is going to be X. If you do a Hermitian again on X, it's going to become X, simply X.
Yes. A Hermitian and X Hermitian.
Yeah. So this is going to be X A Hermitian and
X Hermitian.
and X Hermitian. Right?
Yes.
But A Hermitian, remember A is a skew matrix.
Yes.
It's going to be X.
Which equals A.
It's going to be, it's a skew Hermitian matrix. It's going to be negative A.
Negative.
Which is the same as P minus IQ. Right?
Yes.
Also, we could say that we could swap the negative X and the X. This matrix, because it's a scalar, it's X Hermitian AX, but with a negative in front of it. You agree with that?
Yes.
So looking at this, they are the same, right?
Yes.
This is the same as that. So you can see clearly that if you take this, they are equal. So X Hermitian AX negative, it's going to be equal to negative P plus IQ, right? And then remember, this matrix that you're seeing is also equal to this one. These two, they are equal. So we can also have that negative XH AX equals P minus IQ.
I agree.
Okay. And so
not P minus AQ, minus P minus AQ. And this A negative HAX AX equals P minus AQ.
yeah. That's what I said. Negative XHAX equals P minus IQ.
Okay.
And then negative XHAX equals negative P plus IQ. Right?
Okay.
So
yes,
it means
right.
that the two are equal. So negative P minus IQ must be equal to P minus IQ, right?
Yes.
So this means that negative P equals P, right?
Yes.
And when can a negative number equal itself? It's only when that number is 0.
Yes, I agree. Yes.
So what did we find out? We find out, so P plus IQ is going to be equal to IQ, right?
Yes.
And what is P plus IQ? It was the lambda. So lambda equals IQ. This means that it's purely imaginary.
Okay.
And that's the proof.
Okay.
Yeah.
It was really interesting.
Yeah, it was. The beauty of it is that it's understandable. Yeah. Okay, so we go to problem 2. Show that if you have lambda comma x, these are any two pairs of Hermitian, 2E pairs of a Hermitian matrix A, and lambda is not equal to alpha, then the eigenvectors x and y associated with the distinct eigenvalues lambda and alpha, they are going to be orthogonal to each other. You need to show that xhy equals 0. Do you understand that question?
No. Show that
Lambda x and alpha y are any two E pairs of a Hermitian matrix.
show that if lambda
Okay.
x and alpha y are any two E pairs of Hermitian matrix.
Then the eigenvectors x and y are orthogonal eigenvectors x and y are orthogonal. You just need to show that xy equals 0. I don't know why they're saying that xhy equals 0. Remember, whenever you want to show that two vectors are orthogonal, whenever you multiply them, if you do a dot product on your two vectors, you should get a 0. If you get a 0, then they are orthogonal. So let's follow and see how they have done it. These are any two E pairs of a Hermitian matrix A. So E pairs, they mean that for eigenvalue lambda, the eigenvector associated with it is x. So you could think of that as an eigenvalue and its associated eigenvector. That's why they are called E pairs, E for eigenvalue, eigenvector pair. Okay, so if you have such two eigenvalue eigenvector pairs for Hermitian matrix A, we need to show that the two eigenvectors are orthogonal. So let's try out a solution. So we first note that. So the notes are the information that we are getting from the question. So the fact that we have an E pair, then we must have that if you take A multiplied by a vector X, this should be equal to lambda multiplied by the eigenvector X. Okay. And also the second thing we need to note is that if you do A multiplied by the eigenvector Y, then this is equal to alpha multiplied by that eigenvector Y. Yeah. Okay. So we could multiply both sides by the Hermitian vector Y. We could just take the first equation, AX equals lambda X, maybe multiply that by YH AX. This is going to be equal to lambda YH X. And that is the first step of the proof. Okay. And then we can do the same for the second one. We could just multiply XH by AY. This will be equal to lambda X, not lambda, but alpha XH Y. So we have those two.
Give me a sec. YH AX. Okay.
Yeah. And then next, we can just take the Hermitians. Let me just push this over. So let me write it here. So we've done YH AX equals lambda YHX. And then this one we could say XH AY equals alpha XH Y. And then now we want to take the Hermitians on both sides for the second equation. So if we do that, if we take the Hermitians on both sides, we take a Hermitian there, and we also take a Hermitian on the other side. We are going to get Y Hermitian A.
Negative A.
Let's write A Hermitian.
Okay.
You know, this one is a Hermitian matrix. It's not skew Hermitian.
Okay. It means equals to A transpose.
And then, yeah. And then this one is
Mhm.
X. And then on the other side, we are going to get it's equal to Y Hermitian. It's going to be alpha Y Hermitian X. And that's
Mhm.
that's what we have. But because A is a Hermitian matrix,
Mhm.
this would mean that this is Y Hermitian. A Hermitian
Times
is A.
transpose.
It's just A, right?
Yes,
And then this is
equals the same.
alpha Y Hermitian
Mhm. Times
X.
X. So A equals alpha. But we can divide it by YH times X,
Yep.
both sides.
So let's focus on these two equations. We can look at this one, and then we can look at this other equation, right?
Yes.
Maybe we can subtract both of them from each other.
Mm-hmm.
You see Y Hermitian AX minus Y Hermitian Y Hermitian AX minus Y Hermitian AX is 0, right?
Mm-hmm.
Subtract 2 from 1 to get. So these two, they're going to give you 0 equals, if you subtract these other two, you're going to get Y Hermitian X multiplied by lambda minus
Mm-hmm.
alpha, right?
Yes.
If you divide both sides by lambda minus alpha, you get Y Hermitian X equals 0, right?
If we what? If alpha
If you divide
equals
both sides
lambda?
if you divide both sides by alpha minus lambda, right?
Yes.
If you do that division, alpha minus lambda,
Mm-hmm.
alpha minus lambda, 0 over alpha minus lambda is 0. And then this divided by alpha minus lambda, it's Y Hermitian X
Mm-hmm.
equals 0. And I think that is what they wanted us to prove. They wanted us to show that XH multiplied by Y, it's going to be 0.
Mm-hmm.
Yeah.
But we have YH times X equals 0. We just need to take a Hermitian of this multiplication and we'll have XH times Y, right?
Yep.
Okay.
Yeah. So YHX equals 0. If you take a Hermitian, you get that, which is equal to XH Y.
Mm-hmm.
And so we have shown that the eigenvectors associated with those distinct eigenvalues, their product is 0, and so they are going to be orthogonal.
Mm-hmm.
Yeah. That makes sense, right?
Yes.
Okay. Then we go to the next problem. It's problem number 3. So we have a matrix, a 2 by 3 matrix A. It's shown below.
Mm-hmm.
It could be thought of as a linear operator that maps vectors from R3 to R2. We can write it like that. It is called R3 is the domain, R2 is the codomain. So we have the basis set, the standard basis S1, another standard basis S2. Where is the question?
Consider the matrix A R2 by 3 shown below, so it was a linear operator that maps. Maybe we need to transform from A to R3 to R2. No, it's how this matrix they made. We write this as.
Oh, what is the matrix representation of this matrix? It's a, I think this question is kind of funny. They have given us a matrix A, 1, 0, 1, 0, 1, 1, right?
Yes.
And then they are asking us for its matrix representation. It's going to be itself. A is the matrix representation of itself. Let me see whether they found that to be the answer.
No, they trying to find a matrix from which it was transformed.
Uh-huh. Okay. They take the inverse of the codomain, they multiply by A. And they got something different. That's true. You see what they did?
What I see?
Did you see what they did to get the matrix representation?
Yes. Upper triangle matrix.
Yeah, so matrix representation. Matrix representation A with an inverted comma. It's going to be W inverse, and then you have A, and then you have V.
Mm-hmm.
And how did they get V? Oh, the standard basis. V is S1, and then W is the other standard basis.
Mm-hmm. And they take
So
a negative.
Yeah.
Inverse.
So A is 1, 0, 1, 0, 1, 1, and then W is 1, 0, 1, 1, and then V is 1, 0, 0, 1, 1, 0, 1, 1, 1.
Mm-hmm.
So to get that representation, it seems straightforward. You do W inverse. And W inverse in this case, it's 1101. Its inverse, you multiply by A itself, 101011, and then you multiply by V, 100 110 111. I guess it's straightforward.
But I don't remember this matrix representation formula.
Mhm.
V inverse times A times V. W, I mean.
Mhm.
Inverse W times A times V.
You don't remember looking at it? Maybe they used a different set of letters. Because when you look at the notes, they are saying that the matrix representation of A, actually it's a definition. It's a very clear definition for finding the matrix representation of A when the basis changes. Yeah. So if you didn't see it before, you should make a note of it. Yeah, because for this question, you just needed to use that formula and then you multiply them out. And then in the end, once you are done with your multiplication, you're going to get this representation is going to be 100 100,012 at the end. Yeah.
Okay, yes, I see.
And then the last question is on SVD. I remember you wanted to do some more practice on SVD, right?
Yes.
Maybe you can try using this question without, can you try doing this question without his notes?
Okay, of course.
Without the solution.
Solution, yeah, of course.
And then once you get your answer, you can compare it with with what he did.
Okay.
Yeah.
Okay, I'll do it.
Yeah. I think that was straightforward. I thought the homework was tough, but after doing it, I have found it's not that tough. Yeah. But the solutions made it easy.
Okay, Steven, I got it. I'll do my homework 4 and I'll check it out.
All right. Let me try sending this over.
Okay, Steven.
All right.
All right. Send me please these notes.
Yeah, I'm doing it now.
And see you tomorrow, okay? But I didn't schedule yet, but I'll do it.
Okay. So we'll see you tomorrow.
See you
so tomorrow we
Bye,
proceed
Steve.
with complex analysis.
Maybe we can make a half of. I'll try to schedule 2 hours, half of complex analysis, half of homework assignments. Okay, maybe another 5 and 6. I will send you everything today.
All right. Okay.
Okay. Thank you. Bye.
Okay. Bye-bye.